Okay, this is example 9 in topic 7. So we're going to go over how to draw the shear and moment diagram for this beam that has triangular distributed loading on two ends of the beam and a 3 kilonewton point load on one side as well. Okay, so this is a cantilever beam because it's fixed at one end here, A, and it is free at the other end. So we call this a cantilever beam. And what we're going to do is we're going to start out by drawing the FBD of the system. And I'm going to actually draw it over here off to the side. So this is the this is the fixed end, and then we have the free end over here, B. So this is A, B. We have a triangular distributed load with a magnitude of 6 kilonewtons per meter. And we also have a 3 kilonewton point load at the end there. Now I'm going to go ahead and add the resultants. Each resultant here is 6 times 1.5 divided by 2. So I get 4.5 kilonewtons. I'm going to write the equation over here, right? It's just the area of that triangle. This distance here is 1.5. And then the location of each of these here. This is 2/3 times 1.5, so I would get 1 meter. And then here I would get the 1.5 plus 1/3 of 1.5. So the 1.5 plus 1/3 times 1.5, which would give me 2 meters. Okay. Now this is my FBD. Oh, I'm missing the reactions at A. I also need to put my AX, my AY, and my MA. Okay, now that's my FBD. I can go ahead and sum forces for equilibrium. I'm going to come on the side here. I'm going to sum the moments at A, set everything equal to 0, and assume counterclockwise is positive. So I have the moment at A minus the 3 kilonewton load times the moment arm of 3 minus one of the 4.5 loads times the moment arm of 2 minus the other 4.5 resultant times the moment arm of 1. And if I set all that equal to 0, I get MA equals 22.5 kilonewton meters. If I sum forces in the X direction, set everything equal to 0, I get AX equals 0. And if I sum forces in the Y direction, set everything equal to 0, assume up is positive, I get AY minus 4.5 minus 4.5 minus 3 equals 0, and I can solve for AY as 12 kilonewtons. So I'm going to go ahead and highlight those values here. Okay. All right, I'm actually going to redraw the beam over here before I draw the shear moment diagrams. Okay. I like to use the beam as reference as I'm drawing my shear and moment. And then I have my MA, 22.5 kilonewton meters. And then I'm actually going to draw the whole distributed load again, so I remember to draw the integral of this distributed load when I'm drawing my shear and moment diagrams. So this is 6 kilonewton per meter. Oh, and then I also have my 3 kilonewton. Okay. Now I'm ready to draw my shear and moment axes. I like to put my shear and my moment and the units of each of these. And I'm going to draw my reference lines. So I have a reference line here at the end, and I'm going to draw a reference line here in the middle to show me where everything changes. At x equals 0 right here, initially for V, I'm being pushed up by this 12 kilonewton force. So I'm going to be at 12. Okay. Now, this is where it's a little tricky for a triangular distributed load, so we have to pay extra attention here. This triangular distributed load, I'm going to highlight it, is basically just a line. So you could think of this, the function of a line, is something like y equals x, right? Like if you had a graph, the function of that line would just be, the graph line would be this, and it would just be something like y equals x, if this is the x-axis and this is the y-axis, right? It's just from like algebra or geometry. So you can see that this line is very similar to this line here. So if this function is something like y equals x, and we know that shear is the integral, well, what is the integral of x? Something like x squared, 1/2 x squared, or some constant x squared, right? But it's a second order function. Or a parabola. So we know the shear is going to be a parabola because it is the integral of this triangular distributed load, okay? So that's the first thing. We're at 12. We also know that the area under the load diagram is going to tell us the rate of change of the shear. That's the definition of a derivative integral relationship. So what is the area under this curve? Let's see. I'm going to highlight the curve. To figure out what the rate of change is up until this first orange line, I need the area under that curve. So what is the area under the curve? Under a load curve. What's the area under that load curve up until the first orange line? It's a triangle, so it's 1/2 1.5 times 6, which happens to be the same as the resultant, 4.5. So I know that at this orange line here, I need to go from 12 minus 4.5, which is the rate of change, which gives me 7.5. So by the time I get to the next orange line, which is this reference line, I need to have exhausted all of the area under the curve, which is 4.5. It's going down, so it's negative 4.5. So I subtract 4.5 from 12, and I get to 7.5. Okay. Now, the next step is, how do I connect these 2 points? Now, I know it's going to be a parabola. I'm going to draw 2 options here. It can either be a parabola like this, or it could be a parabola, I'm trying to pick 2 different colors here, let's do green, like this. Okay. How do we figure out which one to pick? Well, we use the slopes. So the slope of this line here, of the shear, is the value of the load. Value of distributed load. So what is the value of the distributed load at x equals 0 right there? Well, it's 0. You can see it's 0. There's no load. So the slope has to be 0. So a slope of 0 is a horizontal line. What's the value of the shear here? Well, it's the full value. We've exhausted that 4.5, or we have 6 kilonewton per meter. It's the full value. So the slope needs to be a high negative value. -6. So the only option I have to connect those 2 lines would be like that. So the shear diagram, I'm going to draw it a little bit better here. We're connecting the 0 slope, the -6 slope. It has to be a concave down parabola. Now, the next side here, I'm going to highlight it. We'll do orange. This next side here, I need to now push down from 7.5 minus 4.5 because that's the area under here. So this area equals -4.5 again. So 7.5 minus 4.5 takes me to 3. okay? And I'm going to start now with a negative slope. So rise over run negative, and I'm going to get to a 0 slope because the load value here is 0. So something like that. And then now I have this 3 kilonewtons that's going to push me down to 0, and that is my shear function. Okay. Now let's go ahead and do the same thing, and let's trace our shear and load diagram to figure out what the moment diagram is going to be. Okay, so we're starting at x equals 0 right here, and we have a 22.5 kilonewton meter moment, and this moment is going to cause concave downbending. So we're going to start by putting the 22.5 in the negative because it's causing concave downbending. Now, we know that we are going to end at 0 because we have to close and we have no moment acting on the rest of that beam. So by the time we get to the middle portion here, okay, we're going to start out with a slope of our line here of positive 12. How did I know that? Because the value of shear is positive 12 at 0. And then we're going to have a slope value of positive 7.5 when we get to the next orange line, which is something like maybe that. So the only way, again, to connect those two lines, this is now a third order function, right? The integral of a parabola is a third order function, or a cubic. Okay. And then we know we're going to have a 7.5 slope and then a 3 slope. So we're kind of just going to continue with something like that. Okay. And here we can see that our M max value is 22.5 and our V max was 12. Okay. All right. So we're going to move along and we're going to now discuss cables and do a couple of more problems for structural analysis that kind of combine all of these topics we've been working on with method of joints, method of sections, and now structural analysis. So we're going to talk about cables, which are very often used in structural systems for transmitting loads. We've already kind of dealt with cables because we've dealt with tension cables in this class already. But here are the assumptions that we're going to make when we're dealing with cables. So we're going to assume that they're perfectly flexible, which means that they don't resist bending. Okay, so they're only resisting that axial tensile force inside of them. Okay, and we're going to also assume that the tensile force acting in the cable is always tangent to cable at the point along its length. Okay, so basically each point of this cable, the tensile force is, for every point, is tangent to those points. Okay. Now, we're going to assume that it has constant length before and after loading is applied. So we're going to assume for this class that these do not extend. Later on in mechanics of materials, we'll deal with this kind of extension and deformation. Okay. And we're going to assume that we're dealing with a rigid system, which means that we don't have any deformation. Okay. The geometry remains the same. All right. So if we look at this system here, okay, what we see here, we have a lot of unknowns. So we have, I'm going to highlight here, okay, we have unknown YC, YD, H, L1, L2, L3, P1, P2, okay. And we also have unknown tension here. So we have 9 unknowns to solve here. This is basically an analytical diagram of something like this, like a traffic light. Okay, so our option 1 is to use the total length of the cable, okay? And we can use Pythagorean theorem to relate these lengths, okay? Or if one of the, we call these sags. Sags is how much the cables sag, okay? If one of the sags is specified, then we can use equilibrium to kind of break up this system and solve for everything else that's going on. So this isn't so different than what we've been doing before, where we've been breaking up systems using method of section and method of joints to solve for what's going on. Okay, so let's actually do a problem like this. Let's do a really similar problem to the one that I just showed you here. And you can see that this is what I was mentioning. If one of the sag lengths is known, then we can use equilibrium to set up a system here for us to solve. Okay, so let's go ahead and figure out what our unknowns are here. So I'm going to draw an FBD off to the side of this system. Something like that. So we have these known loads. We have here a pin at E that's going to resist some EY, some EX, and then the same here, we have some AY resistance and some AX resistance here. Okay, so basically we have how many unknown support reactions? We have 1, 2, 3, 4 unknown support reactions. Okay, but we also have unknown cable tensions, right? We have these 4 cables and we also don't know the tensions there. And we also don't know YD or YB. So let's list our unknowns out because these are starting to get excessive. So let's come over here. What are the unknowns? The first set we have are reactions. So we have AX, AY, EX, and EY. The next set we have are cable tensions. This is 4 unknowns. And we have 4 cable tensions, right? We have 4 cables there. And we also don't know the sags, 2 of them. So we don't know YB or YD, and this is another 2. So we basically have 4, 8, and 10 unknowns total here. So we know that we have to split up this system at quite a few different points here to solve for what's going on. Okay, now we can start off by looking at the whole system here. And let's just go ahead and start by summing forces. So this was the FBD. We'll work off this. Let's sum forces in the X direction, set everything equal to 0, and say this direction is positive. We end up getting negative AX plus EX equals 0. Okay, not much we can do there. That's pretty much all we can do. This is equilibrium for the whole system. Let's try now summing moments about point E. You can do E or A, doesn't matter here. I'm just going to pick E. And we get negative AY times a moment arm of 18 plus 4 times a moment arm of 15 plus the 15 kilonewton force times a moment arm of 10 plus 3 times a moment arm of 2. And we actually can directly solve for AY because AX goes through the point that we're rotating about, and we get 12 kilonewtons. And now we can sum forces in the Y direction. Add all of those up, we get 12 minus 4 minus 15 minus 3 plus EY, and we get EY equals 10. So I'm going to highlight this here, what we found, and we do have this equation that we can use for later. We can't do anything with it now. Okay. Now what we can do is we can start separating this system. So if we want to kind of start analyzing this, we can separate each cable. So we can start by separating this green cable that I just highlighted. Okay. And let's kind of just redraw that cable right here. We have point A, where we have our AX and our AY, so we know this is 12 kilonewtons. We don't know what AX is. And then we know we have the 4 kilonewtons here, right? We had 4. And what happens here is because we're cutting at this point, we have this cable force that's being exposed in this direction right here in this direction, right? So we'll have this kind of T, and I'm going to call this, that's B to C. I should probably put these on here to make it easier. That's TBC, so I'm going to call that tension from B to C. And it acts at some angle with the horizontal, some angle theta BC for cable VC. And then the last piece of information that might be helpful is that this length from here to here is given as 12 meters. And that's actually my YC. Actually, sorry, all the way down is 12, not that one. All the way down to the tension is 12, not just to the point. This is 12. This is equal to YCB. YC, we'll call this. Okay, this is a known value. So what we can do here is we can use equilibrium again now. So we can sum for some moments about point C. Let me write down here what's going on. This is point A, this is point B, this is point C. So we can sum moments about point C. We can set everything equal to 0. Counterclockwise is positive. And we get AX times a moment arm of 12 minus 12, this 12 kilonewton AY, times a moment arm of 8 plus the 4 moment arm of 5. And we end up getting that AX is equal to 6.33 kilonewtons. And actually we can take this number now and we can put it back into this equation. I'm going to unhighlight it, and we get that EX is also equal to 6.33 kilonewtons. So we've solved for a couple more unknowns by making that extra cut. Okay, we're not totally done. We can still kind of pull some more information out of this FBD here. So we can sum forces now in the X direction, set everything equal to 0. We have TBC cosine theta BC minus the 6.33. We can't solve for anything there, but we can continue with our equilibrium. And we can say that 12 minus 4 minus TBC sine theta BC equals 0. Now we have these two equations, two unknowns here. 1, 2, we have the TBC theta BC. And we can solve for those two equations, two unknowns, and we get theta BC equals 51.6 degrees, and tension in cable BC is 10.2 kilonewton. We didn't really need the theta, but we needed the TBC, so, okay. All right, so we're getting closer to solving for everything here. We have used kind of the method of sections here. We're going to use the method of joints now. So we're going to isolate joint A, or point A of the system. And here, point A, it's this guy right here, point A. We know we have the 12 kilonewtons going up. We have the 6.33 now that we solve for AX. And we also have the TAB that we're releasing now. So we're trying to figure out this guy here, this tension here, TAB. And TAB acts at an angle of theta AB. And remember, we have to kind of remember the previous topics here. When we're doing method of joints, we are able to use two equations. Moment doesn't work anymore because there's no moment arm. So it works because we have two equations and two unknowns, theta and t. So if we set up our sum of forces in the X, we get TAB cosine theta AB minus 6.33 equals 0. Can't solve for anything yet, but we set up our Y and we get negative TAB sine theta AB plus 12 equals 0. So we end up solving two equations, two unknowns again. Theta AB, we end up getting 62.2 degrees. We didn't need that, but we can use it to solve for our TAB of 13.6 kilonewtons. Okay, now just two more of these analyses. Let's isolate point C here. which is right in the middle. We can use that tension that we solve for. So this is point C right here. We would have TCD in this direction. And at this point, it might be a good idea to stop the video and see if you can actually solve for this on your own, since you've seen it a couple of times now. Okay, and then of course we have theta CD, and we know that this was a 51 point, where did we solve for it? 51.6 right here, theta BC. So we still have our two equations, two unknowns that we can set up for this. So now we have TCD cosine theta CD minus 10.2 cosine 51.6 equals 0. Sum of Fy, and we get TCD sine theta CD plus 10.25 sine 51.6 minus 15 equals 0. We get theta CD is 47.9 degrees and TCD is 9.44 kilonewtons. Okay, last point we have to do, point E, to solve for our last tension, TED. That tension right there. And we have, what do we have at point E? We have 10 going up, right? EY, this is EY. I'm going to put that as 10. And then we have EX, which was 6.33. And then, of course, we have this tension that we're looking for, TED, and it acts at an angle of theta ED with the horizontal. We're good, two equations, two unknowns, so summation of forces in the X equals 0. We have 6.33 minus TED cosine theta ED. And then we have summation of forces in the Y is 0, up is positive. 10 minus TED sine theta ED equals 0. And we can solve for theta ED equals 57.7 degrees. And our last unknown tension, TED, of 11.8 kilonewtons. And we have solved for all our unknown tensions and all of our unknown reactions this way. Okay? All right. So the last thing we're going to cover in this video are some extra topics to show you kind of what we can do with the structural analysis portion and what you might be doing in your future classes in civil engineering. So cables are super important because we subject them to distributed loads, and one of the most important applications of this are cable systems on bridges. So if you've driven down a suspension bridge like this picture that I'm showing you, you might have seen a cable that is supporting a distributed load like this one. So we have our real world model right here. This is the bridge. And this is an analytical model of a bridge like that, where you would see this tension cable and it's supporting this kind of distributed load. So this is very similar to the analysis that we did previously with those point loads. This just has a distributed load upon it. Okay, so what we can see here is, let's consider that this cable has no weight to it. Let's consider this cable here that's subjected to a distributed load, and let's assume that the cable is weightless. Okay, so let's draw our FBD. Okay, let's draw the FBD here of what we're trying to show of this cable system. Okay, so we're going to start here. This is that cable, right? And we have some type of distributed load on that cable. So for some small portion of this, let's say we isolate some small element, okay, like this delta x that we're showing here, some small element, okay, this whole element would be delta x, let's say. I'm blowing it up to make it look a lot larger so that we can see what's happening for this small, teeny tiny differential element, delta x, okay? That's delta x, and we know that based on arc length, we can call this arc length delta s. So that little delta s would be this little arc length right there, okay? The length of the cable. And for that distributed load, we would have W of x times delta s, the length of the cable, right? And since we're making this teeny tiny little cut here, we would also have some tension going from this end. And we would also have some tension, but well, it should be, remember the tension's tangent to the cable, tension plus some change in tension to the next side, depending on the load. And we would also say that this is delta x here. We have some delta y. The cable has some delta y, some height change, right? And of course, this T acts at some angle theta, okay? And if that acts at some angle theta, then this angle here is some theta plus some change in theta, delta theta, right? This is a differential element. We'll call this point O right here, our initial point, okay? And we have our Wx delta S, and we have also the last item here is the distance, we'll call this little O our origin, the distance that Wx delta X, the resultant, acts away from O, is some K, some proportion of delta X. K is just a proportion. So we know that the resultant acts some proportion away from delta x, okay? So now if we're going to apply equilibrium to this FBD, okay, we have sum of forces in the x direction equals 0. This direction is positive. We would get negative t cosine theta for our t down there. And then we would have the t above, so t plus the change in t, cosine of theta plus delta theta equals 0. And we could do the same thing for the y direction. We would have negative t sine theta minus w of x, delta x, plus t plus delta t, sine of theta plus delta theta. And we can use our last equilibrium equation about point O, that origin point that we defined. Counterclockwise is positive, and we get Wx delta S, right, times K delta X minus T cosine theta delta Y plus T sine theta delta X equals 0. And if we divide everything by delta X, and we set delta x to approach 0, like we would with a differential element, we end up getting d times t cosine theta divided by dx equals 0, and d times t sine theta divided by dx minus w of x equals 0. And we can divide the two. We know that dy dx equals tangent of theta, right? So what we're going to do here is we're going to integrate. Let's say we integrate this expression. We would get t cosine theta is equal to some constant when we integrate, okay? We're going to call this constant fh, okay? Why are we calling it fh? We're calling it FH because we're going to call this the horizontal component of the tensile force at any point on the cable. Okay, and then we're going to integrate the second expression here. And you can probably see where this is going. Okay, we would get t sine theta equals the integral of wx dx. And then we're going to integrate this again. Okay. And we get y equals 1 over fh integral of the integral of wx dx dx. Okay. And this is a special function that we just derived. Let me box this off. Okay, and it's used to determine the function of a curve of a cable. Okay, basically used to determine y equals f of x of the cable. Okay, we can apply boundary conditions to solve for this horizontal component fh and all of the constants of integration there. Okay, so I have an example here for you to try. Okay, this is a cable of a suspension bridge that supports half of the uniform road surface between the two towers A and B. And if the distributed load is given as W naught, what is the max force that's developed in the cable and the cable's required length? And this is all in terms of L and the sag length H. So I have this all solved out for you here. So why don't you try solving this based on this derivation that we went through and see if you can get the same solution that I get. I started out with the derivation that we just did with this formula here for determining the function of the cable, and you can actually integrate the function, and then you're going to get your two constants of integration, C1 and C2. And what you need to do from there is you need to use boundary conditions to solve for your constants of integration. Okay, so what that means is that if we look at the problem, at x equals 0, our y value is also 0. So we can plug in our 0, 0 point here. Oops, here we go. Our 0, 0 point as our first known. And then we also know at x equals 0, the derivative of y with respect to x is also 0, because at this point that we've chosen here, the slope of that function is 0, right? Horizontal line. Okay, so that's our origin point in the center, and that is also where the derivative is equal to 0, the slope. So we can plug these two in. These boundary conditions we solve for C1, C2 is equal to 0. So the function of our curve looks like this, and we're able to determine that maximum force and the cable's length requirement there. Okay, that is it for this topic. And this video is, or this is the last example in this video.